I'm presenting our paper, Heterogeneous Private Information Retrieval, and this is a joint work with my advisor, Amir, from University of Massachusetts, Amherst. Private Information Retrieval, or PIR, enables clients to query and retrieve data from untrusted servers without these untrusted servers learning what data was retrieved. A simple example would be a patient who wants to know more about diseases, and he's worried about his privacy. So we can use PIR to query a medical directory, which is untrusted, and retrieve these information. There are several applications introduced for PIR. For example, you can watch a movie from a movie streaming service without the server knows what movie you are watching. Or you can retrieve Tor relay information from Tor directories without leaking any information. Or you can find your friends in a messaging application without the messaging application server knows about your contact list and other applications. There are two major types of PIR. The first category of PIR protocols, they can be run on a single server, and they provide computational security. That means their security is based on a very difficult mathematical problem that the untrusted server cannot solve in polynomial time. For example, integer factorization. And because these protocols, they use cryptographic assumptions, they are a little bit slow. On the other hand, we have other PIR protocols that they are needed to be run on multiple servers. And they have this big assumption that these servers are not colluding. And usually, these protocols are providing information theoretic security. Our focus in this paper is on multi-server PIR protocols. And as you can see, all of the existing multi-server PIR protocols, they assume that the PIR servers involved in the protocol, they have computation, they have similar computation and communication constraints. So in these protocols, the client will impose uniform computation and communication load on each one of the servers involved in the PIR protocol. But in real-world scenarios, it's different. Some of the PIR servers, they are more resourceful, and they have more communication and computation resources. So these, and we call these all of the existing multi-server protocols homogeneous. And these protocols are not suitable for these applications. Let me show one example. For example, if we want to use PIR in a content delivery network, suppose that there is a client who wants to download some articles from New York Times server, and he knows that the New York Times is publishing its data on a CDN. So if he wants to use one of the existing multi-server PIR protocols, he will send some queries to the origin server and some of the queries to the closest CDN server. But as you can see, the query size, the answer size, and the computation is uniform. It's symmetric. But the goal of the CDN is not that. The goal of the CDN is to offloading the computation and communication burden from the origin server and bring it to its network. So these homogeneous PIR protocols are not suitable for these kind of scenarios. So our goal in this paper was to design a heterogeneous private information retrieval that the client can impose non-uniform computation and communication load on the servers. So for example, in the previous example, if the client can use an HPIR or heterogeneous private information retrieval, he can send a very small query to the origin server, which is New York Times server, and retrieve a small portion of the data from that server, and then sends a huge query to the CDN server, which is very close to the client, and retrieve a big portion of the data from that server. And by doing this, the computation load would be much more on the CDN server. So we need these HPIR protocols for such an examples. In our paper, we show that by using HPIR or heterogeneous PIR, we can increase the usability of the applications for current PIR scenarios, and we even introduce new scenarios for using HPIR. Let me show you another example. For example, suppose that there is a client who wants to download some files in torrent in a private mode without leaking any information that what kind of files he is downloading. And he knows that there are some seeders in the network with different resources. So based on their resources, he can send different size of queries to each one of them and retrieve the files in a private mode. Now that we know that HPIR or heterogeneous PIR is necessary, I am going to show you how we build our protocol. First, in most of the PIR protocols, they assume the data server has a database of R records, and each record has C elements, and each one of these elements is a member of a finite field. So if the client wants the Jade record, he will send a query of R bits that all of the bits are set to 0 except for the Jade position. So if the database server multiplies this query to the database metrics, the result would be the record J. But the challenge is how to make EJ private. There are several approaches in PIR area, and we use secret sharing in our work. One of the simple secret sharing we have is Shamir secret sharing, that the dealer can share a secret S among L shareholders. The dealer will hide the secret at x coordinate 0, and he will find a polynomial of degree t that supports this point, and then send 1 point to each one of the shareholders. Now, if more than t shareholders gather together, they can construct this polynomial using Lagrange interpolation, and they evaluate the polynomial at point 0, and they extract the secret. Goldberg used Shamir secret sharing to design his PIR protocol. And in his PIR protocol, there are several non-colluding servers. And the PIR client acts as a dealer, and the servers are acting as the shareholders. In his protocol, the client will break the query into query shares and send, and the client will send each query share to one of the servers. And each server will multiply the received query share to the database metrics and returns the result. And as you can see, the query size, the answer size, and the computation is similar for all of the servers. So this is a homogeneous PIR protocol. We designed our PIR protocol similar to Goldberg's PIR by replacing the Shamir secret sharing with our PIR-tailored secret sharing. In our PIR-tailored secret sharing, the dealer can share multiple secrets from values of zeros and ones among shareholders. Values of zeros means that in the PIR protocol, the client is not interested in those records, and ones means that the client is interested in that record. And we name this secret sharing PIR-tailored because it's not designed to enable recovering the secrets by the shareholders, because in a PIR scenario, the PIR servers are the shareholders and they are not trusted. They are maybe adversary. And we design our secret sharing by increasing the degree of freedom of the secrets by injecting more random numbers. We use more than one prime number in our system, and we attach each one of the secrets to one of the prime numbers. In our PIR, our HPIR protocol, the client will break its query to multiple query shares, and the client can retrieve more than one query. more than one record. So for retrieving queue records, the client will break the query into queue plus 1 shares. And then based on how much resource each server has, it sends different number of query shares to them. For example, here the server 1 has less computation and communication resources, so the client will send just 1 query share to that server. Or the client is sending 2 query shares to the server 2, and the rest of the query shares to the other servers. So the client sends different number of query shares to each one of the servers based on their resources. And after receiving the query shares, each server will multiply the query share to the database metrics and return the results. And as you can see, because the number of query shares that are sent to each one of them is different, the computation and the answer size for each one of them is different too. We implement our design in C++ with 800 lines, and we use NTL library for handling big number operations. Our code is compatible with PIR-C++ PIR library, and all of our experiments are run on a single thread on a machine with 3.6 gigahertz frequency. This slide is showing the computation time on the servers. We compare our protocol with Goldberg's. His protocol is a homogeneous. And the main scenario in our protocol is that we have 2 servers. One of them is rich server, another one is poor server. The rich server is more resourceful. It has more computation and communication resources. And our goal is to put most of the load on the rich server. So when the client is retrieving just 1 query, our protocol acts like a homogeneous. So our protocol costs a little more than the Goldberg's, is slightly more than Goldberg's PIR. But when we are increasing the number of queries, the computation time on the rich server will increase, but on the poor server, it remains fixed. And this slide is showing the communication cost of our protocol. We have a parameter in our protocol called degree of heterogeneity that the client can tune it to show how much load each server should have. This figure is an example that the client is retrieving 31 records, so it has 32 query shares. At the start, the client is sending 60 query shares to one server, 16 to another one, so it is acting like a homogeneous PIR. And the communication cost is slightly more than the Goldberg's PIR. But when the client is changing the degree of heterogeneity, it is sending more query shares to the rich server and less number of query shares to the poor server. So upload bandwidth, download bandwidth for the rich server increase, and the upload bandwidth and download bandwidth for the poor server is decreasing. And we also use a technique in our protocol that for minimizing the upload bandwidth for the poor server, we use a pseudo-random number generator. So the client can send just a seed of pseudo-random number generator to the poor server, and the poor server can construct the query on its side and then multiply it to the database metrics. For conclusion, in our paper, we show that all of the existing multi-server PIR protocols are homogeneous, meaning that the client will impose symmetric computation and combinational load on each one of the servers. We propose heterogeneous PIR protocol, and we design the first and HPIR, and we implement it based on our PIR-tailored secret sharing. And we show that with HPIR, we can increase the usability of the current applications for PIR. And we also introduce new applications for HPIR. And our code will be available at this URL. Thank you.
So have some time for one quick question.
Hi, thank you for the talk. Two questions. The first is, if I understood correctly, if you assume different powers for different servers, can't you just use the standard PIR, the Goldberg ones, and increase the number of shares? For instance, if a server is more powerful, you just give 2 shares. So you consider that server as, say, 2 servers, and do this just in this naive method, or what's that doesn't work in?
Because Goldberg's PIR is based on Shamir secret sharing, and it's like in Shamir secret sharing, you send 2 shares to one person and 1 share to another person. And if the privacy level it remains fixed, you are increasing the ability of one of the shareholders. And
I see.
It's different from that,
Right.
because actually you are increasing the privacy level without increasing the previous privacy level.
Okay, thanks. And the other question is, I mean, of course, you have to keep this information about servers. I'm the most powerful server, right? So how do you authenticate this information? I mean, someone can pretend to be the most powerful server and collect more queries than others. And also, if I'm the most powerful server, most likely everybody is sending queries to me, and after a while I will become kind of weak because I will not be able to answer all those ways. So how do you handle all these dynamic changes?
For example, in our example, PIR over CDN, the New York Times is publishing its data on the CDN, and the purpose of using that CDN is offloading the computation and communication load from the origin server. So the main reason for using CDN was to put all of the computation on the CDN server, and they are paying the CDN for doing that. So I think the best answer would be that in the PIR over CDN, the CDN is prepared for more queries for computation because New York Times is paying the CDN for these kind of computations and communications.
Thanks.